And the camera woman here is Meng Li. And now we're mounting laser diodes modules for field campaign in Ivory Coast. We hope to monitor the insect abundance as function of height in the tall jungle canopy. And we're making 2 modules. This one here is for polarization lidar. So what we have is a polarization beam splitter here that we can control here. We can adjust it here. And we have a half wave plate here to spin the polarization of one of the diodes. And then here we're going to mount 2 identical laser diodes. Alright, so the polarization of this laser diode will be spun 90 degrees. Okay, so the way we do it is we have these custom made small laser mounts here. They're milled out in aluminum by a small workshop south of Lund. And then we have the actual mount here. That is the anode, so plus, and then we have the cathode coming here. You can see over here we have the small laser diode. So I simply peel off the wire here.
What's that wire? The canal?
What?
What is this wire?
That was not so professional, but because
Cut it off.
cut it here like this, and now I now need to loosen a bit here. The cable is fixed with a screw, and just to get it all the way in so that the plastic is not protruding. Like that. Okay, good. Oops, now when I screw it in, it comes up and up. It's a homemade laser mount. It's mainly because any of the commercial laser mounts are too bulky. Okay. I just put some tin on the wire here. So in this case here we are mounting near infrared 808 nanometer laser diodes, and they have a power of 5 watt. Alright. So far so good. This one is fixed. So now I'm going to take a laser diode over here. These type of laser diodes are called C-mount laser diodes. It has nothing to do with the camera mount. It's just this format of lasers. Okay. Alright. So most of this so-called laser diode here is just a piece of gold-coated copper and something of brass, and then it has a apparently big hole in the center here for an M2 screw. So that has nothing to do with this, is just metal. And to be able to see the laser, it's mounted on the edge of this piece of metal here. Exactly. And you can maybe see a small fiber and some glue. This is called a fast axis collimation lens, FAK lens. FAK, not
Yes, yes, yes,
not,
yes, yes,
not the other.
yes.
Yeah. Okay, this small, you can see that there's a small polished part here of the mount with a small edge. So this allows us to put the laser right into the edge, and so the laser diode then becomes in the center. And what this fast axis collimator does is that it reduces the divergence in one direction. So in this case here, these laser diodes, they are small line sources in one direction. It's important when you do this that the smoke goes upwards and not in front of the, otherwise it can condense on the lens, right? I'll just cut off the remainers here. Alright. So now it's mounted here. So in this case here the line has this direction, and the divergence of the light is now something like plus minus 8 degrees, which is also more or less the F number of the expander, which means that we hope to collect and collimate.
Light coming out this way?
Light is coming out straight upwards. Yeah. And if you image the source, it's gonna make a line in this direction.
Okay.
And the polarization also have this direction. I mean, the textbook and that all laser diodes have this direction or that direction, but it depends on the manufacturer and the crystal organization of the laser. So it could be different for different models of lasers. In this case, polarization is like that, and over here we have a half wave plate. And when we turn it correctly, when this says fast axis here, turn correctly, then we will turn the polarization 90 degrees. And that allows us to combine two lasers here, with one of them have a wave plate and the other doesn't. So you can combine it with a beam splitter here, which is polarization beam splitter. Now, all this module here, it's important to mount these two lasers the same way. You can see here, they're both mounted the same orientation. And it's also important to have, when you make scheimpflug lidar, it has a preference for S polarized light. So we're not splitting, analyzing the polarization on the detection side here. We're multiplexing on the emission side. So that means that on the detector we have a linear polarizer, which only allows the S polarized lights to reach the detector. And now we can then change here between co and depolarized light. And light depolarizes, for example, when it enters the abdomen of an insect. And it can depolarize, for example, if you have a pregnant mosquito, that's showed by the New Jersey group. Whereas if you hit a wing with the resonant wavelengths, then you can get copolarized. You can get very fast flashes of light from these thin wing membranes. Yeah. All right.